Venus is often called a sister planet to Earth due to its similar size and rocky composition. However, the similarities end there. Its surface environment is extraordinarily hostile. The planet is shrouded in a thick atmosphere of carbon dioxide, covered by dense clouds of sulfuric acid that reflect most sunlight, making Venus the third brightest object in Earth's sky while completely hiding its surface from view. What secrets lie beneath this endless cloud cover? Surprisingly, beneath its glowing facade is a landscape shaped by volcanic activity and forces that remain only partially understood. Only recently have modern instruments begun peeling back these mysteries, revealing landscapes and phenomena more complex and active than anyone had imagined. Venus is no longer just an enigmatic neighbor of Earth. It's a planetary puzzle, patiently awaiting its next discovery. It all began in the 1970s and 1980s. As part of the Soviet Venera program, spacecraft managed to withstand the planet's extreme conditions long enough to capture the first images of Venus's surface. In 1975, the landers Venera 9 and Venera 10 endured the crushing pressure and extreme heat just long enough to transmit the first photos from the planet's surface. Harsh black and white panoramas of a rocky plain. A few years later, in 1982, the Venera 13 and Venera 14 probes sent back the first color images of Venus's surface, revealing brownish rocks and soil beneath an orange sky. These pioneering landers revealed a landscape of fractured stones and flat slabs, strikingly similar to Earth's, though they survived only about an hour before succumbing to the planet's hellish environment. Nonetheless, their cameras proved that landing and photographing Venus was possible, allowing humanity to glimpse this hidden world for the first time. While the Venera landers provided a ground-level view, a complete picture of the planet's terrain came from orbital radar mapping. In 1990, NASA's Magellan spacecraft entered orbit around Venus and used synthetic aperture radar to systematically pierce through the planet's thick cloud cover. Over the course of 4 years, Magellan mapped approximately 98% of Venus's surface in high resolution. By bouncing radio waves off the surface, scientists were able to uncover astonishing details of its topography and geology. Towering volcanoes, vast basalt plains, winding rift valleys, and deformed highlands known as tesserae. Magellan's radar images reshaped our understanding of Venus, revealing a surface shaped by volcanism and tectonic deformations, with relatively few impact craters. Furthermore, Magellan detected signs of extensive volcanic formations and even hinted that volcanic activity might not be dormant. Later, fluctuations in atmospheric sulfur dioxide levels led scientists to suspect that active eruptions could still be occurring. The mission's success demonstrated the power of advanced technology at the time and laid the foundation for future explorations. Since visible light cameras cannot see through Venus's perpetual cloud cover, scientists developed indirect imaging techniques to map and study the surface. One of the most powerful methods is radar imaging, which Magellan used so effectively. Radar waves in the radio-microwave spectrum easily penetrate Venus's thick clouds and atmosphere. These waves bounce off the solid surface, then return to the spacecraft, carrying information about reflectivity and elevation. By processing the return signal, scientists can create detailed images of the surface, even in complete darkness. Soviet orbiters Venera 15 and Venera 16 first used this approach in the 1980s, mapping about a quarter of the planet's northern regions. Magellan then redefined the technique to cover nearly the entire planet. Radar mapping revealed numerous geological details that optical instruments could never capture from orbit. Circular coronae formed by upwelling magma, long lava channels, mountain ridges, and impact craters, all of which became visible in radar images. In essence, radar sees the texture and shape of Venus's surface, and that enables scientists to create 3D topographic maps and even assess surface roughness or composition. For example, high radar reflectivity at mountaintops suggests the presence of metal-rich frost. In short, radar became the key to unveiling Venus's hidden face, transforming what was once a featureless white sphere about the size of Earth into a mapped world of mountains, valleys, and volcanoes. Another invaluable indirect method is infrared spectral imaging, particularly useful for studying Venus's night side. As we've established, the dense atmosphere is mostly opaque to visible light, but there are a few narrow windows in the near-infrared spectrum where carbon dioxide and clouds absorb much less radiation. Spacecraft can use these windows to detect heat emitted by the planet. For instance, the ESA's Venus Express spacecraft, which operated from 2006 to 2014, carried an instrument called VIRTIS, Visible and Infrared Thermal Imaging Spectrometer. This device observed Venus in wavelengths around 1 micron, which can penetrate the lower atmospheric layers. From Venus's nighttime hemisphere, VIRTIS detected the faint glow of hot surface rocks. By measuring the infrared radiation emission ability, in essence thermal infrared brightness of different regions, scientists gathered information about the surface's composition and temperature. This was a clever way to indirectly see the surface. In fact, Venus Express used infrared emissivity maps to identify anomalous hotspots on volcanoes such as Mat Mons. These hotspots had distinct spectral signatures, indicating relatively unweathered and therefore fresh lava flows. In 2010, a study was conducted based on VIRTIS data. It yielded an exciting conclusion. Some of these lava flows could be geologically young, possibly just a few thousand years old, practically yesterday in geological terms. This data provided some of the best evidence at the time that Venus is still volcanically active. This evidence was dramatically confirmed in 2023 when researchers reanalyzed Magellan's 30-year-old radar images and discovered an actual volcanic eruption captured in the early 1990s. They found that a volcanic vent on Mat Mons had visibly changed shape and enlarged between Magellan's mapping cycles, indicating an eruption and lava flow during those periods. This radar-based before and after comparison is the most direct proof yet of ongoing volcanism on Venus. The implications are profound. Active volcanoes could be releasing gases into the atmosphere even today, potentially explaining mysterious fluctuations in the atmospheric composition, such as variations in sulfur dioxide levels. Additionally, Venus Express and other orbiters used infrared and radio occultation techniques to determine temperature and chemical composition at different atmospheric heights, another form of indirect atmospheric imaging. The success of infrared sensing demonstrated that even without direct visual observation, we can still learn a great deal about Venus's surface and lower atmosphere by scanning it in the right wavelengths. But more on that later. Together, radar and infrared techniques have laid the groundwork for even more advanced approaches in future planetary exploration. After the Magellan era, Venus exploration quieted down, but the 2010s and subsequent years have seen a revival with new technologies, sometimes as part of missions not originally intended for Venus. One of the most unexpected contributions came from NASA's Parker Solar Probe, designed to explore the Sun. During its gravity-assist flybys of Venus, scientists turned its cameras towards the planet shrouded in thick clouds. And surprisingly, Parker's Whisper Imager managed to capture the first ever visible light images of Venus's surface from space, photographing its night side. Venus's cloud-covered surface is usually hidden. Parker's camera, sensitive to the near and far infrared wavelengths, detected faint thermal emissions from the planet's scorching surface. The images revealed subtle bright and dark regions corresponding to continental highlands, plains, and plateaus, features visible only because the probe observed Venus's night side, where its heat could be detected through the clouds. This unprecedented achievement demonstrated that even an instrument that wasn't specifically designed for Venus studies could be useful under the right conditions. Around the same time, ESA's Bepi Colombo and the joint ESA-NASA Solar Orbiter made close flybys of Venus on their way to their primary targets, Mercury and the Sun, respectively. In October 2020, Bepi Colombo passed by Venus and captured stunning black and white images of the cloud-covered sphere using its small monitoring cameras. During two subsequent flybys in 2020 and 2021, Bepi Colombo also used its scientific instruments to study the planet's environment. Its sensors observed Venus's magnetic and plasma surroundings and even detected oxygen and carbon atoms escaping from the upper atmosphere. They were recorded in a previously unexplored region of the magnetosphere. This finding confirms that solar wind stripping was a key process in Venus's history, likely responsible for removing large amounts of water and other volatile gases over time. Essentially, Bepi Colombo caught Venus in the act of losing atmospheric atoms, which was crucial for understanding how the planet transformed from a potentially water-rich world into the dry greenhouse that we see today. Similarly, the Solar Orbiter, which flew past Venus in December of 2020 and again in August 2021, used its onboard instruments to collect additional data. It performed high-cadence plasma and magnetic field measurements on the planet's night side, as Venus lacks an internal magnetic field. This offered insights into the induced magnetosphere created by the solar wind. While Solar Orbiter's main cameras were pointed at the Sun, its detectors recorded phenomena such as Venus's magnetotail and ionized gas during flybys, contributing to our understanding of how the planet interacts with solar radiation. 5 years earlier, in December 2015, Japan's Akatsuki spacecraft, known as Venus Climate Orbiter, finally entered Venus's orbit, carrying a set of specialized cameras to study the planet's dynamic atmosphere. Akatsuki's instruments cover wavelengths from ultraviolet to infrared, and that allows it to observe multiple layers of Venus's atmosphere. For example, its ultraviolet imager tracks high-altitude clouds, while infrared cameras can peer deeper, detecting heat from the lower atmosphere and surface on Venus's night side. With these tools, Akatsuki continuously monitors weather on Venus in an unprecedented way, something that no other mission had managed. Notably, shortly after reaching orbit, Akatsuki's instruments detected a remarkable feature: a massive stationary bow-shaped cloud structure stretching almost from pole to pole over Aphrodite Terra. Scientists interpreted this as an atmospheric gravity wave, not to be confused with gravitational waves, caused by air currents flowing over Venus's mountain terrain. This was unexpected, as it suggested that surface topography directly influences high-altitude atmospheric flows. Additionally, Akatsuki observed winds similar to jet streams. In the lower and middle cloud layers at the altitude between 28 to 37 miles, it discovered a fast equatorial jet with peak wind speeds near the equator. This finding, along with the long-term tracking of clouds in an infrared and ultraviolet wavelengths, helped unravel the mystery of Venus's atmospheric superrotation, a circular pattern that makes the entire atmosphere spin around the planet in just 4 days. Waves and atmospheric tides driven by differences in solar heating likely transfer momentum and sustain this rapid motion. Multispectral imaging has also enabled the creation of a 3D map of the atmosphere's structure over time, revealing how temperature and cloud composition change with altitude. By working across multiple wavelengths and over several years, this long orbiter has shed new light on Venus meteorology. So how were all these discoveries made? Different parts of the electromagnetic spectrum reveal different aspects of Venus, and these missions leverage this fact. In ultraviolet light, Venus's cloud tops display patterns of bright and dark shapes, including the famous large Y-shaped dark feature drifting around the equator. And these patterns result from an unknown chemical absorber in the clouds that strongly absorbs UV radiation. And so, ultraviolet imaging that was first used by spacecraft like Mariner 10 and later Akatsuki reveals the dynamics of Venus's upper atmosphere, including fast-moving winds and turbulence that would be visible in regular lighting. In the near-infrared range, specific wavelengths become critically important. On Venus's night side, these UV windows allow thermal emissions from the surface and deep clouds to be detected. Instruments tuned to these wavelengths can identify hotspots and even measure surface emissivity, as Venus Express did. At slightly longer infrared wavelengths, we can see the silhouettes of lower and middle cloud layers, helping track cloud movements and detect changes in opacity or chemical composition, such as variations in gaseous sulfur dioxide. The thermal infrared range is useful for measuring cloud top temperatures and detecting thermal anomalies. For example, Akatsuki's long-wave IR camera maps Venusian cloud temperature distribution day and night, revealing atmospheric waves and circulation patterns. Finally, at the far end of the spectrum, microwave and radio waves enable radar imaging and subsurface probing. Radar waves, ranging from centimeters to decimeters in wavelength, easily penetrate Venus's thick clouds and reflect off solid ground, as demonstrated by Magellan, which produced detailed radar images of the planet's geology. In future missions, ground-penetrating radars will allow scientists to peer hundreds of yards below the surface. By combining these multi-wavelength observations, researchers can construct a complete and nuanced picture of Venus, and that will ensure that no layer of the planet remains hidden from our view. After decades of insufficient exploration of Venus, a new wave of missions is on the horizon, equipped with cutting-edge imaging systems that will finally provide answers to many lingering mysteries. NASA's approved 2 ambitious missions, Da Vinci and Veritas, scheduled for launch in the late 2020s, while the European Space Agency is developing the Envision project for the early 2030s. Each mission has specific scientific objectives and is outfitted with state-of-the-art instruments that build upon past experience. Da Vinci, Deep Atmosphere Venus Investigation of Noble Gases, Chemistry and Imaging, is a combined flyby and atmospheric descent mission. Around 2031, the Da Vinci carrier spacecraft will release a robust descent probe that will plunge into Venus's atmosphere. As it descends, it will directly measure atmospheric composition, searching for noble gases and chemical clues about the planet's formation and evolution. A key question is whether Venus once had oceans of liquid water. Da Vinci will analyze argon, krypton, nitrogen, and other gases to find traces of an ancient ocean or past climate condition. Notably, as it nears the surface, the probe will capture the first high-resolution images of Venus since the Venera missions, focusing on Terra terrain, heavily deformed highlands that may be analogous to Earth's continents and could be among Venus's oldest rock formations. Da Vinci's cameras will take detailed images of these rugged, blocky landscapes in the final miles of descent. This could confirm whether Tesserae contain traces of ancient water or unique minerals, and whether they record a time when Venus's geology was more Earth-like. Essentially, Da Vinci will combine direct sampling and direct imaging, something no U.S. mission has done since the 1970s, potentially transforming our understanding of how Venus became the world it is today. At around the same time, the powerful orbital mapper Veritas will be launched. Upon arrival, Veritas will enter Venus's orbit and conduct a global high-resolution surface survey. Its primary instrument is a state-of-the-art synthetic aperture radar system, which will create topographic maps and radar images with far greater detail than ever before. Veritas will generate 3D topographic maps of almost the entire planet, detecting features as small as 15 to 30 yards compared to the 100-yard resolution of Magellan. This means mountains, faults, craters, and lava flows will be mapped with unprecedented precision. Thanks to its interferometric synthetic aperture radar or INSAR capabilities, Veritas will even be able to detect subtle changes in surface shape over time, such as volcanic inflating or fault line shifting. This could indicate active tectonic or magma movement. One of the mission's goals is to determine whether Venus experiences processes like plate tectonics or active volcanism by identifying such changes and counting fresh volcanic structures. In addition to radar, Veritas carries an infrared spectrometer that will map the emissivity of surface rocks, providing clues about their composition. Different rock types, such as basalt and granite, emit infrared heat differently, allowing the spacecraft to create geological and mineralogical maps of the planet. At night, it will search for thermal anomalies, which could indicate active lava flow or warmer ground, and it will monitor volcanic gas emissions by detecting localized spikes in water vapor or other gases in the atmosphere above active sites. Essentially, Veritas will significantly enhance the data set from previous missions, with sharper eyes and new senses to finally answer questions about Venus's surface. Is Venus' crust static or churning? How does it release heat without Earth-like plate tectonics? Its findings will also complement Da Vinci's data. For instance, while Da Vinci's descent probe will capture close-up images of Tesserae, Veritas will reveal how widespread and elevated these structures are and whether similar regions exist elsewhere, with signs of past water-driven deformation or even ongoing activity. Following NASA's missions, ESA's Envision orbiter is set to arrive in the 2030s, equipped with a comprehensive suite of instruments to tie everything together. Envision's primary goal is to provide a holistic study of Venus from its inner circle to its upper atmosphere, with a special focus on the connections between geological activity and atmospheric changes. To achieve this, Envision will carry several instruments, including an S-band radar called VINSAR provided by NASA. This radar will be used for targeted high-resolution surface imaging, as well as polarimetric radar and radar altimetry for topographic studies. VINSAR's resolution will be within a few yards for specific regions, and repeated imaging will allow it to detect surface changes over time, such as new lava flows or landslides. Envision will also carry spectrometers as part of the VIN-SPEC suite, operating in ultraviolet and infrared wavelengths. These will search for volcanic gases like sulfur dioxide in the atmosphere and map the mineral composition of the surface, observing variations in infrared emissivity and reflectivity with greater sensitivity and spatial resolution than Veritas. Uniquely, Envision includes a subsurface radar sounder, which will be used for the first time in the history of Venus. It's capable of probing up to a mile beneath the surface. This instrument will allow scientists to study layers of rock and sediment deposits, potentially uncovering underground channels, subsurface structures, or the thickness of weathered rock layers. Finally, Envision's radio silence experiment will measure Venus's gravity field and internal structure, as well as conduct radio occultation studies of the atmosphere to determine temperature and pressure profiles. By working together, these instruments will help answer key questions such as: is Venus currently geologically active? How do surface and atmospheric processes interact? Did past eruptions influence climate, or did climate change drive erosion? How did Venus diverge so dramatically from Earth? Did Venus ever have continents or oceans? Envision is essentially a synthesizing mission, built on the legacy of Magellan, Venus Express, Akatsuki, Da Vinci, and Veritas to create a unified understanding of Venus. Today we stand on the verge of finally understanding why our sister planet, so similar in size and origin, took such a drastically different path, becoming a world with a furnace-like surface and an acidic sky. Perhaps these discoveries will one day help us prevent a similar fate for Earth. Or maybe they will reveal a way to reverse the process and make Venus into Earth 2.0.